Cloud recording now. Okay, so you should see the thing in front of you that says, "Oh, by the way, it's being recorded." So I'm going to go ahead and continue. So where we stand is just we've finished up some of regression. We're going to do a little bit more with regression, and then that's sort of the goal of today, finish up the concepts. But as you work your way through the sample exam questions, I'm sure you'll bump into some additional questions about regression, even ANOVA. And it seems that if I look carefully, chapter 3 is largely about ANOVA, but we're recasting ANOVA in a different way. Okay, so I'm going to sort of say chapter 3 is all about ANOVA, but we'll look at it in a new way. It's almost as though you're looking at a building, then you walk around halfway around the building. Could you see the building looking a little different? Yeah, it's still the same building, but the view that you have may be greatly enhanced. Your understanding what the building's like would be greatly enhanced by the additional bit of information in chapter 3. And that's the last of the bit of info that's going to be on the exam. So that's my spiel about where we're at, where we're going to. Maybe if you all have questions related to administrative matters first, that'd be great. And then we'll go on and talk about questions related to regression and then sort of dovetail into finishing up our understanding of regression. So, um, questions about administrative stuff? Who's got them? Will you have an answer? I already have an answer to the practice exam. So thank you, Melissa. Marissa, what was I reading? Marissa. But I haven't posted the study guide answers yet. I plan on doing that right around Friday. And the reason is Friday morning. That way you guys could come by office hours on Friday if you want to talk about it. And I don't encourage everyone to take the exam over the weekend, but if you want to, that's fine. But certainly, office hours on Monday would be another good opportunity to double check your understanding thoroughly before taking the exam, and that's by Tuesday at noon, right before this next class set. Not next class, a week from now, basically. Okay, so another question, and if you sort of talk aloud versus in the chat, um, it may allow for those that are watching this video later to hear your question, not just hear me read your question.
I had a question.
Sure.
So can you just talk a little bit about timing, how that will work for the test? I know that we're timed.
Okay, so yeah, what is the nature of the Canvas-based exam? Now, probably most of you, if not all of you, have done a test administered via Canvas in the past. So if you look at the instructions for how the test will work, it should say something like you have 50 minutes to do this test. I think the instructions are already online, and with those 50 minutes, all you got to do is answer the questions. Now, a couple things I would want to stress is print out in advance that blank, not blank, that sort of set of scratch work. Because if you want to provide an answer, rather than typing an answer into Canvas, which includes equations, which is always really challenging, just write on a piece of paper. The piece of paper I'll provide to you, just say, oh, this is about question 5. Okay. And so I'll know exactly where to look, okay, for additional information that will help me give you either full or partial credit. Now, some students have even on past exams written my answers over there on paper, and then they upload their piece of paper, and I'm going to grade that. So the test would be 50 minutes. I usually set the timer for something like 53 to 55. And the reason is different people have different internet speeds, or the server might be operating more slowly for one of you than for another. And it will never be perfect. I'm sorry, I can't control that. But I can say if I give you an extra 3 to 5 minutes, there should be no problems. But another part of the instructions are, if something weird and freaky happens, let me know. We'll deal with it. Okay. I've had students who've let me know that partway during their exam, the entire internet for them just disappeared. And when they tried to log back into the exam later, it said, I'm sorry, your exam is finished. You missed the opportunity. And so I was able to negotiate, not negotiate. Well, okay, I negotiate with Canvas what to do, but I was able to sort of give the student an appropriate way of continuing on with the exam. But it's often on a case by case basis. So there's that. One other bit of information is I like to write questions such that you don't have to open any data sets at all with JMP or Minitab or whatever. You literally should not have to open a data set at all to answer it thoroughly and properly and completely. Some of you, however, have gotten in the habit of using JMP, and that's fine. Go ahead and use the tool if you know this is the tool, here's how to use it, I can get my answer quickly. That's great. I'm happy with that. Okay. So any data set that I use to produce a question, if I have access to the actual raw data, I'll provide you the raw data in such a way that you can use the tool in the way that you've used in labs. You're also welcome to use the lab activities from the past. Just, if you remember instructions for how to get something done in the lab, go ahead and use it. But I would definitely recommend having an 8.5 by 11 piece of paper, maybe two sides. One side is list of ways to get JMP to get you what you want to get it done. So, okay, yeah, sort of analyze, fit Y by X, here's my X, here's my Y, and then click on the test for equal variances. Okay, so that would give you something like Levine's procedure. Okay, so just having that sort of cheat sheet lying around to get the software to do what you want it to do might be helpful. Again, I'll provide you everything you need to answer the questions completely. But if you want to use the software, having no frustrations with trying to spend time remembering how to get the job done would be good. Second, along those lines, on the other side, you could perhaps have a list of equations, when they would be used, how they could be used, and an example of how to write up your interpretation of any of those results. And keying off of past homework solutions might be a good place to go for that. Okay, might be a good place to go for that. Okay, so Anise, I think I answered that question pretty thoroughly. Someone else want to ask a follow up on that? Administrative sort of how does the test work thing? Okay, how about any questions related to regression as a method in terms of what you've understood so far, or perhaps not understood and would like to understand at this juncture?
I was just wondering if you could talk about the question 28 about brain activity on the homework.
Okay, so yeah, that's one that in theory you've turned in already, but if I remember it correctly, it deals with people who play the violin or viola or some sort of stringed instrument.
Mhm.
And the notion was the amount of time that you play the stringed instrument may be related to the brain activity. And I'm going to answer this without opening the data set at all, but rather entirely on sort of in a whiteboard sense. Okay. So my presumption is you've got data values and something like there's a people with the years of brain activity X of 0, and there's quite a few of those, if you will, the control group. They're not string players. And BA for brain activity is your X variable in years of, Y is brain activity, X is years. And what we saw was something like that sort of a pattern. Now, I don't remember the pattern exactly, but this is close enough. Okay, so if I were to draw a trend line through the data, and we'll see in lab later today that that trend line is sometimes called a least squares line because it comes up with the best way of predicting y from knowing x. If I tell you x, can you tell me y? If I tell you how long a person's played a stringed instrument, can you tell me what their brain activity would be? That's really sort of the xy relationship. And that xy relationship is b0 plus b1 times x. And the underlying model is that y itself, yi, the ith value of y, is beta 0 plus beta 1 times xi plus epsilon I. And we're going to really focus in on the model just a little bit today. But the slope in the population is beta 1. So one way you could answer this question, I think, is to test the hypothesis that beta 1 is equal to 0, or perhaps on the other hand, it's not equal to 0. Because if beta 1 is 0, it says that the brain activity doesn't depend on the number of years a person's been playing a stringed instrument. If the slope is 0, it really says flat. So as x changes from low to high, from 0 to 5 to 10 to 20, there would be no change in the y level, the brain activities at all. So the slope being 0 says no relationship. Okay, another approach that a person could take, and I like this approach, but another approach that a person could take is we've got two groups there and there. And if you want to talk about the average level of brain activity, I could denote that mu 0 and a mu s for the stringed instrument players. And I could use a t-test to deal with the null hypothesis that mu 0 equals mu s, or the other hand, mu 0 is not equal to mu s. But that's in the context of a t-test. And I don't like that approach as much because it gives up some information. It's just saying, hey, we've got two groups. Some have been playing the stringed instruments for a number of years, and others have not at all. And we're just going to compare the two averages. Valid, but my approach that I'm suggesting here with the slope is A, depending on a linear relationship, and if there is a linear relationship, then my method is better. It's more likely to actually catch a relationship if there really is one. We could say it's a more statistically powerful technique. Okay, so I think that's a hint of two separate ways, both of which are reasonable, and my statement of my preference. So, Anise, does that answer the question you had?
That does. Thank you.
Anyone else want to follow up on this question, the strings and the brain activity?
Yeah, I'd like to follow up
Yeah,
for a more
please.
practical question. So in this example, we wanted to test whether the slope was equal to 0. I was having trouble figuring out how to test if the slope was equal to a different number using JMP.
JMP doesn't do that as cleverly and cleanly as you'd want.
Mm-hmm.
Let me show you how you could approach that, though. So I'm just going to go ahead and clear that. And suppose you've got a belief, and this is comparable to something I see with regularity in economics as one discipline. Now, there are other disciplines where this happens as well, but in economics, for whatever reason, they care about whether the slope is 1 or not. It relates to whether something is elastic or inelastic, sort of magic buzzwords in some profession that many of you don't even care about. But if the demand curve is steeper than a slope of one, or the supply curve is steeper than a slope of one, it means one thing theoretically, or less steep than a slope of one, it means a different thing entirely in terms of the behavior of the market. Okay. So I want to test, is the slope one, or is it, say, greater than one? My null hypothesis is that the slope is one. On the other hand, the slope could be exceeding one, greater than one. I said that wrong. Greater than one. Now, the general form of the t-test for a slope is the sample slope minus the theoretical slope according to the null hypothesis. And I'll call that beta 1 comma 0 to remind myself that that's according to the null hypothesis. You're going to plug in that value there and divide through then by, well, I'm not even going to bother changing back to the color of black. Divide through by the standard error of B1, the sample slope. So that's going to form a t distribution, and if you use then the t table, you could get a p-value from that.
I
So
see.
does that answer your question, Morgan?
So then practically you'd actually need to create a like another column for that B minus beta value.
No. You have in the output, and I'll just show you right now a data set that I was going to use in terms of class later today. So why not start with that? Let me see if I can find the right data set that I want to go with. Not that vanilla. That's from a different class. That's ice cream. Although I like ice cream, it's not relevant to this discussion. Okay, so I'm just gonna that smallify and smallify. And I'm gonna go with, oh, here's a good data set. We have data on the corn yield in one county in Illinois for each and every year from 1890 to 1927. So, you know, this is like the history of crop science example. Do you think that over time technology or scientific innovation would allow for extra yield per acre? I would think so, especially during the golden age of agriculture or whatever. Let's look at the data. Under analyze fit y by x, I'm thinking that the yield may depend on the year in which the data were obtained.
Are you trying to
this is-
show? Are you
Go
trying
ahead.
to show your screen?
Oh, I'm sorry. Yes, I was. So let me go ahead and share that screen.
Thank you.
Yeah, go ahead and share. Yeah. Oh, okay. So now that I am showing you the screen, and thank you for mentioning I'm a moron. But no, but seriously, that's the sort of thing that your instructors all the time, we screw it up, we're gonna forget that, and no one minds you telling us, or if they do, oh my gosh, that's someone who's wound too tightly. So yeah, the yield of corn may depend on the year. You can make the argument from ag that if there is an increasing yield across the years, it may be due to technology or science or something like that. If I were to go with analyze fit y by x, I then am going to say yield may depend on the year, click yay. And I've got my plot, adding now my trend line to the plot. You can see a slight positive trend. Is it statistically noticeable or not? One thing we're going to find downstairs at the very bottom is the slope of year. So in other words, for each year that goes by, we have an extra 0.149 as the yield in our data set. Is this 0.149 in the slope of the data so steep we're convinced that it's real? Okay. My standard error is 0.0605. That ratio, the slope over the standard error, gives you my t ratio. If we wanted to go with a different null hypothesis, it's going to be still found via that as B1 and that as the associated standard error of B1, and the t statistic T is B1 compared to what you expected it to be according to the null hypothesis, beta 1, 0, over then the standard error for B1. So that is your t statistic that you could use, and use then a t-table to get your p-value and conclusion, much like in that earlier revision section where we use the t-table to get after a p-value.
Thank
So I
you.
think, Morgan,
That
that,
clears it up. I appreciate it.
yeah. Anyone else? Okay, so what I want to do is dive right in, and I know that next time it's fine to ask questions about regression, but I would encourage you, if you have regression questions, rather than ask them at the beginning of class next time, let me spend more time focusing in on chapter 3, the newest content, and maybe any additional regression questions could be handled via office hours, or maybe towards the end of class on Thursday. That way we'll make sure we give adequate coverage to the material in chapter 4. So regression. Yeah, we just want to know, hey, is there a linear trend? Well, when I put the word linear within parentheses there, it's because I'm assuming with regression or least squares that the trend, if there is one, is linear. It might not actually be, and we'll learn in a later chapter how to fix a problem if there is a lack of linearity. But basically, simple questions like, could I, and the forestry people sometimes say, oh, yes, you can predict the age of a tree within a species based on the diameter of the tree at about 4 feet high. Yeah, literally, if you go hug the tree as a tree hugger, and you could then calculate how thick the tree is, the diameter of the tree, and within a species, okay, in specifically one location within a species, there's a great way of predicting then the age of the tree from just the height or the thickness of the tree at about 4 feet elevation. Okay. The method of doing that would be collect data and then find the trend line. And it turns out that the scatter plot's approximately linear. I could call this a graph of means, if you will, and let's maybe use our example here on corn yield and the rainfall data. I'm going to remove my trend line. Can I remove my trend line? No, I'm just going to go ahead and redo it without a trend line. Fit y by x, and by the way, the recall button is your friend. Notice that when I just hit recall, it repopulated my X and my Y and other things inside of a potential analysis. And so if your analyses get complicated and you only want to make little changes, just get in the use of hitting the recall button. So I've got my scatter plot here, and my gut feeling approach is it's going to be easy to come up with a graph of averages. And by that, I mean the following. If I say to myself, for the year 1900 to 1910, what is the average value of yield? Now you're thinking there's that one value down at the bottom, but most of them are up high. Here's the average. Okay, what about 1910 to 1920? Well, the average is right around there, 1920, 1930, the average is there. 1890 to 1910, oh, the average is there. And if you sort of connect those dots, that would be a graph of averages. Regression is found by essentially taking that graph of averages, okay, and stretching it out and making it smooth. Any method like a graph of averages could be viewed as a regression, okay? But when we fit a straight line via that graph of means or graph of averages via the least squares approach, and we'll talk about that in the lab today, we're minimizing the vertical errors. In case of the tree predicting its age from the diameter, we want to minimize the errors in predicting the age of the tree. If I'm using least squares for this regression line to predict the yield from the year, for any given year, like 1905, I can read up and there is the actual yield. But here's down here, according to the trend line, what I predicted yield would actually equal. How far off was I? I would want to take those errors and minimize the sum of those values once squared. Okay. And moving forward a little bit, we have a collection of things which, if all true, and we'll learn in chapter 8 how to check them, or maybe we'll do some of that even before chapter 8, but in chapter 8, by then we will finalize with checking then these assumptions. And I sort of think when looking at this example, it's maybe when looking at this situation, it's best to think about an example. And so the example I'm going to encourage you to think about is something like y being the height. I'm sorry, x being the height of a person and y being the weight. And so if I were going to say x equals height, and I'm just thinking in inches because it's, freedom units, and y is the weight, and again, pounds, we're more comfortable with that in most cases for humans. So I have here the basics of a trend line. The portion that I've just emboxed, is that a word? The portion that I just put inside of a box is a straight line relationship. And it says, if you tell me a person's height and you multiply by a slope and then add to that an intercept, you have a typical value of the person's weight. But there are these other little awkward things, those epsilons. Those awkward epsilons are departures from average. So what I'm thinking here is there is a typical XY relationship that's in the box, and epsilon is departures from typical. I am 5'8.5". That's my height. 68.5 inches is my X. If I knew beta 1, the slope of relating heights to weights, and then added beta 0, the intercept for the height weight relationship, the linear trend, that would tell me what I should weigh if I was average weight for someone of my height. My epsilon, my error, is how far above average I am. Now, the fact that I am heavier than average for someone of my height means that my epsilon is positive. People who are lighter than average for their height, they would have a negative value for epsilon. Epsilon says how far off you are from the average weight of someone of your height. Now, what do we require to be true? Each statistical method out there has a set of assumptions or beliefs, which, if true, will allow us to hit a conclusion. What we require about regression in this simple linear regression model are that the epsilons will follow a normal curve. And we know how to check for normality. We just don't know how to figure out what the epsilons are just yet, but we'll talk about that later. The epsilons are on average 0. Yay, I could do that. There is a constant spread around the trend line. The data points are above and below the trend line, but they are not getting wider for some x's than for other x's. And independent of each other, let's rephrase that. If I tell you my neighbor David across the street, who's 5'2", if I tell you his weight and you know David has a negative epsilon, that doesn't help you predict my epsilon at all. That knowing one epsilon doesn't help you predict any other individual's value for epsilon at all. That corresponds to that last assumption. Now, if all that is true, then I can go ahead and test a hypothesis. And you do get the output showing you your t value, your p value that corresponds, and we're good to go. Let's look at the example. Oh, hold on. That was not what I wanted at all. Let's find there. Get JMP's output. Again, spotting downstairs in my output. If I can mouse over here, good. So I have my slope for year. Again, that is my slope. The corresponding standard error gives me a t ratio and thus a p-value. Because this p-value is below 0.05, I say, yes, there is a relationship. That conclusion is based on assuming a collection of things which are plausibly true. We'll later learn to verify that they are for any given data set. Any questions about any of that so far before I move forward a little bit more? Okay. So with the time that we have before the lab starts, I want to sort of dive into primarily the standard error equation. Okay. And then we're going to talk about how we could have two separate confidence intervals. And then ultimately, we'll talk about unusual points and our number that sometimes is determined or called R squared. Okay. So our standard error, here is the equation for the standard error. The standard error of the slope, the number that JMP reports to you, that standard error right there, JMP gives it to you, in this case, 0.0605. It's based on, well, n, the sample size, which tells me the larger the sample size is, even if these other numbers remain the same, the larger the sample size is, the more precisely we know the slope. And does that make sense? More data is good. More data gives you more precision, yeah? Secondarily, this number S sub x, that literally is the standard deviation of the x's. And to illustrate that concept, I want to try showing you two graphs, and you tell me in which case it's easier to describe the XY relationship. This is sort of like going to the optometrist. When you go to the optometrist, sometimes the optometrist asks A or B, which one's more clear? I'm presuming two identical XY relationships. That was meant to be two identical looking XY relationships. And if there is a true relationship out there between X and Y, there. And if you have data points that are widely spread across the range of X's, like in A, that's about 20 data points. Or would you rather have all 20 of your data points in a very narrow range of X's? In which case is it easier to tell the XY relationship? In which case is the slope easier to say, I understand it precisely? My claim is when you have the data more widely spread apart in terms of the X values, it's easier to see the slope with great precision. Here I can say for sure the slope is positive because it's a definite trend. But let me erase some things for B and let's verify that it's hard to actually see the slope as being positive. If I gave you the same number of data points, but in a very narrow range of X's, I'm thinking a lot of different possible trends could actually fit through those data. Maybe here is a true trend line. Oh, sorry. I apologize. I erased some of my data. Let's put the data back. Now here is a possible trend line that could fit through the data. Here's another one. There's another one. They all would fit about as well, yeah? Let's rephrase that in terms of heights and weights. Is it easier to tell height-weight relationship among adult males if you have some short guys and some tall guys than if every single one of the people in your data set is 5'9"? If everyone's 5'9", you can't even tell an XY relationship. Okay, So that seems to be, in my mind, two of the three things. The first two are the more obvious. What is this number S sub E? S sub E is the square root of MSE. Sometimes it's called RMSE. The root mean square error, and the lab today defines it, but let's just tell you what it is anyway. It's a measure of how close a data point tends to be to the fitted trend line. It's sort of like a standard deviation, almost. The typical distance between a data point and the trend line is RMSE, the root mean square error. And my claim is if S sub E is smaller, the standard error is going to correspondingly be smaller. So again, let's do one of those optometrist sort of charts, a pair of two situations, and you tell me which is easier to see the XY relationship in. Can you more easily see the XY relationship if the data are quite widely spread, or if they're very narrowly spread around some actual trend line? Same trend line in both cases. Which is it easier to spot the trend? I'm thinking when there's very little variability around the trend, it's easier to spot the trend. Smaller standard deviation around the trend line, the more precisely we know the slope of that trend line. S sub E. The smaller it is, the more precision we have. Okay, that's the standard error of the slope. A couple more things that I want to make sure you see before too long. I'm going to sort of put on hold now statistical versus practical significance. That's something that we will certainly address as we go. The quick summary is statistical significance means simply, is your p-value below 0.05? Can you spot a trend? Practical significance says, hey, if the trend were this, would you care? If I tell you the nature of the XY relationship and you say, oh yeah, that matters to me, that's of practical significance. I cannot determine practical significance for you in your area of study. You all have your own area of study, and you all then know what sort of a difference between the groups or what sort of a slope would actually matter in your discipline. Okay? And statistical significance is what we want to attain. And we'll see in a later chapter, chapter 5, building on some of the concepts in chapter 3, we can design a study that is going to be able to likely spot as statistically significant something that you think is of practical significance to you. Okay, so moving on. Unusual points. There are three sorts of unusual points that we would want to talk about. Three different natures of what it means to be an unusual point, and maybe I'll blankify the screen so I can have a better background to work with. There we go, and then there. So for the unusual points, there's three ways of describing an unusual point. One is a large residual. And so you're thinking, heck, the residual is how far away from your group average you are if it's ANOVA. In regressions context, the residual is how far away from the trend line you are as an individual. The person with a large residual for the height weight sort of conceptual data set is either very heavy for someone of their height or very light for someone of their height. They're unusual relative to someone of their height, far away from the trend line, if you will. Large residual says something like, we've got the bulk of the data, but that one has a large residual. Very unusual data point, large residual, far away from the trend line. What about high leverage? High leverage data points are data points which are unusual relative to the X value only. And if I remember back to when I was a kid, we had these things called teeter-totters or seesaws. You may remember them. Some kids these days don't actually have experience playing on them, but I always thought they were fun. And the reason I actually enjoyed them a lot when I was a kid is because I was really into the preschool version of physics. Most of you were doing the same thing because you're in grad school. Remember when you had like three kids right near the middle of the seesaw, and then one kid at the other far end, and you thought, "Oh, that's cool that we're able to balance. How could that work?" Point of balance, right? Remember physics? Okay. So the average location is the point of balance in a statistical graph. Okay, so if I have a collection of x, y values, okay, if I tell you x is there, the high leverage points are the ones that are sort of far to the right and far to the left. High balance, literally far away from average. In fact, the term that we use to measure leverage is literally h sub I. And if you're someone who's done matrix algebra, it boils down to the diagonals off of a particular matrix that we call the hat matrix, hence the H, and the I refers to which item it is down the diagonal. The further away from the average X you are, the larger your leverage is. So high leverage and low leverage. And it's not really a low and high as though there's a cutoff, but the zero leverage is right there. The further you are away from X bar, the higher your leverage. So let's now talk about influential points. And that is really where we sort of focus. An influential point is one which, if I removed it from the data set, the slope would change dramatically. My predicted value of y for that x would change dramatically. There's a couple different ways of phrasing influence, but what it boils down to is to be influential, you need to have a large residual and high leverage. For example, I have a trend line here. Here is an unusual data point in terms of its X value, high leverage, but because that trend line goes right through that influential data point, even if I remove that data point, the slope wouldn't change at all. Okay, so an unusual trend or data point, okay, but on the trend line, not high leverage. What about a different unusual sort of data point? Low leverage, but large residual. Okay, so here's X bar, large residual, but low leverage. If I had a trend where all the data points are following a perfectly linear trend line, but this one data point that's unusual, it's well outside the range of the X values, the XY relationship data points that we see. If I include this data point or not, least squares or the regression trend line are going to be with about the same slope. If you ask yourself, what is the line that best goes through the data without that trend, without that data point, you'd say, there it is. If I include this data point, it's going to drag the whole trend line up, but not that much because there's only one of them. One unusual data point, large residual, yes, but low leverage doesn't change much of anything. What about a data point that is high influence? Well, maybe think something like this. Very definite trend, very easy to spot. But if I have a high leverage data point that is off of the generic trend line that matches the rest of the data values, including this data point is going to take the line that we had, and I'm going to draw it in yellow. Here's sort of the line that we would have had without including that data point. But we're going to, because we include this data point, to minimize the sum of the squared errors, we're going to have the data point, if you will, not the data point, but the trend line would have to go through it. Essentially, it's not like a rotation per se, but almost as though relative to the X bar location, which is not changing at all, we're having the trend line change its slope dramatically to minimize the sum of the squared errors. Again, that's the topic of the lab today. Any question about leverage or influential points? Or perhaps residuals and their impact?
So with the leverage, does it affect, I mean, obviously we're focusing more on slope, but is there also focus on the change in the y-intercept because of the change of the slope?
I'll say yes, but we tend to focus more on the slope than on the y-intercept as a conceptual way of explaining the concept. In more regression problems that I bump into, we care about the slope than we care about the y-intercept. If you do care about the y-intercept, if it makes some difference in your field, I mean, in finance, one thing that I know of is the intercept in a trend line of one particular y versus its x is called sometimes beta to correspond to beta 0, the slope. And that beta corresponds to the drift in the share price of a stock over time, or something along those lines. I'm not sure I'm remembering it precisely because I'm not a finance guy. But what I'm saying is if you were to fit a trend line, then the intercept, if it matters to you, Josh, you would care about whether the intercept is impacted. Most cases, we care mostly about the slope. What you might want to think about is not so much just the slope or just the intercept, but the collection of values y hat, the predicted values from a linear trend. And if the set of predicted values change as a whole, or if an individual predicted value that you care about changes, that's really what we care most about. And that's always related to leverage. Any individual data point, the leverage and the residual of it give us the influence. So does that clarify it all, Josh? And I'm calling you Josh. I should say Joshua because you put that
No,
on your
Josh is
screen.
fine. Yeah, that's perfect. Thank you.
Anyone else? Okay, so let's see if there's one other thing that I want to hit on before we dive into the lab. Oh yes, there is. There's definitely two separate confidence intervals that will come up with regularity in your life as junior statisticians or people who deal with data. I mean, if you're ever going to be doing a data analysis as the person who collected it, you're often going to say, I'm not the statistician, but you should be prepared to at least know that two commonly asked questions are found in regression, and there's a confidence interval for each of those questions. One of the confidence intervals makes a lot of sense to people right off the bat. Tell me about the slope. Now, the slope tells me or describes the typical XY relationship, literally. For a unit change upwards in X, how much does Y change? That's the interpretation we give a slope. My question is, what is that slope? If I determine that a slope is statistically noticeably differing from 0, I might want to know what is that slope. My sample slope plus or minus 2 standard errors is my way of telling you what that slope is. This is a reminder of back to that earlier chapter. Remember the revision section where we did a confidence interval for the difference of two sample means? This is just that same form. Let me clear that, move it over, and describe that concept. Here we have our estimate plus or minus margin of error, MO. My sample slope is an estimate of the unknown true population trend line slope, plus or minus, and I'll just say plus or minus 2 because I'm sloppy, times then the standard error for that sample slope. Now, if I go up and down two somethings, two standard errors, you should think that should have about 95% confidence. If you want to be precise, use the t-table. Usually 2 is very close if you want 95% confidence. But that's like the following. And think heights and weights again. The canonical example that I like to use for regression the first time through or the second time through even is X being heights and Y being weights that correspond to the heights of those individuals. I want to know how many pounds do you get per extra inch of height? That's the slope beta 1. That's pounds per inch. That's the it's going to be expressed in units of pounds per inch. And so if I'm comparing men that are 5'11" to men that are 6 foot tall, they're 1 inch taller. The 6 foot tall folks are 1 inch taller than the 5'11" people. Beta 1 tells me how much heavier on average the 6 footers are than the people who are 5'11". It's in pounds. The slope is in pounds per that 1 inch of increase in height. Okay, so if I tell you it's about 5 plus or minus 0.5 pounds per inch, you'd think, aha, I know for each extra inch how much heavier people are. That's the slope. That's a little bit different from that trend. The typical value of Y for a given X. The typical value of Y for a fixed X, if X was a particular value, X of P, that's like a height, say 5'3", that's a guy that's a bit shorter than average. If I tell you that that is his height, 5'3", you could multiply by pounds per inch, okay? And then add the intercept to tell me the typical weight of a person who's 5'3". That's a different question. The first question is, how many pounds do you get per inch? The second question here is, what's the typical weight of a person who's 5'3"? Different question entirely. But if your question is, tell me about the typical Y value for a given X, you're going to use this second form. And I'm thinking it's really easy. You plug in that X, multiply by the slope, add the intercept. That gives you your estimate, plus or minus 2. And let's see if we can grab onto things inside this root that form the standard error. And there's one, shoot, I apologize. This is S sub E, or better yet, maybe I should rephrase that, RMSE. Times RMSE. That was left out of the equation. I apologize for doing that. Okay, so the standard error is there within the parentheses. And the RMSE is a measure of precision in the data around the trend line. And you're thinking more precision around the trend line. Of course, more precisely, I can let a person know what the average weight is for any given height. If RMSE is small, it means people have very little variability in weights around the average weight for someone of their height. If RMSE is small, of course, the overall margin of error would have to be small. N also plays a role here and here. And you can see if N were to grow larger, we've got more precision. If I have thousands of data points rather than just 20, I'm going to know much more precisely the average weight of someone of any given height. Of course, N has to play a role in telling you the average value of Y for a given X. But this one little wrinkle here looks unusual, but it actually makes some sense. You've all heard of extrapolation and heard that it's bad to extrapolate too much. Even if the linear model is true, the numerator here, before I square it, describes how closely your height is to the average height. Someone who's 5'3" is a lot shorter than average. Average is 5'10". Someone who's 7'1" is a lot taller than average. How far away from average is this person? And even a slight change in the slope from there to there is going to have a huge impact on a really short individual's predicted value of y. Right at the average, there is very little impact. For very tall people, again, a sizable effect. Small changes in the slope will have a greater impact on how much error there is because the person is far away from average. So how far away from average are you? That's really the concept here. How far away from average are you? We're measuring it in terms of, let's just say leverage. X minus X bar over the standard deviation squared. You could call that leverage. So how far away from average X are you? The larger it is, the less precision our trend line has. The closer it is to extrapolation rather than interpolation. Okay, I think that's a good place to stop for now. There is guaranteed a full-on extra course called Stat 524 for people that want more information about regression. And I'm going to say for many of you, it will be very beneficial to take that class if you find yourself doing a lot of work with problems like those that we're going to be tackling for the rest of this term. That Stat 524 class will be, well, we're just scratching the surface. They're going to go in greater depth, considerably so. And so if you find that this class gives you some, but not all of what you need for your ultimate career goals in terms of understanding how to analyze data, 524 is a highly recommended course. So I feel always guilty at stopping at any point in time in chapter 2. I'm sorry, I'm going to feel guilty. You probably don't care, but I feel guilty. And if you have any questions, in office hours is a great place for me to point you the right direction to answer your question, even if it's not specifically addressed in the homework problems related to chapter 2 or sample exam questions. Okay, so where we stand is I want to put you in your breakout rooms so you can work on the lab activity for the day today. It's all about least squares, and to get you ready for that, I'm going to release stop showing you the screen. How do I do that? Okay, where is that? Okay, here it is. Good. I'm going to stop sharing the screen, and I'm going to sort of, while getting you ready for those breakout rooms, I'm going to mention Carl Friedrich Gauss, G-A-U-S-S. If you've heard of the Gaussian distribution, it's named after the same Gauss as came up with least squares. He's the one who mathematically determined the method that is used in regression. And you're going to be exploring that in today's lab by trying out various different possible slope and intercept combinations and figuring out the errors associated with any given slope intercept pair. And you'll figure out indeed that regression does better than any other values you could try out. So with that in mind, I'm going to open the rooms. If you have questions, flag me and I'll pop on over and we'll get them answered. So, and like normal, some of you are maybe not going to be automatically put into your room. Just tell me where you want to go and we'll get it done. We'll see you in a bit. Some of you are disappearing, but a whole bunch of you are not yet. Okay, so someone tell me where you want to go.
I think I need to go to group 6.
Jack 6.
No, Jack 4.
Jack
Jack goes
4.
to 4. Yeah.
Jack could be in 4. Who want to be in 6?
Harrison.
And
Harrison.
me, Anise.
Anise and Harrison in 6.
Can you put Chase in 9?
I forgot one of you. Later. Chase goes to 9, you say? Chase 9?
Yes,
I'm
please.
gonna go, yeah, he's there in 9. And Harrison, I forgot where you're supposed to go.
6.
I don't even, it looks like, oh yeah, got it. You're gonna be moved to 6. Good. Good.
Thanks.
And someone else?
Nicole,
Uh,
3.
Nicole 3. You know, I figured out it's people who sort of have their Zoom account tied to their Cal Poly email address. It get automatically assigned. Those that don't, and you might have multiple email addresses. So we could deal with that later. So someone else?
I think I'm-
Ali 10.
Ali 10,
also Joe to 10.
Joe 10,
Martika.
Martika 10.
Yeah, all 3 of us.
Yay.
I think
Okay.
I'm with Ted in group 7, but I'm not sure if that's the right group. I'm with
Yeah, I don't know which one I'm in here.
I think it's 7. It's with Roxanne and Morgan, wherever they are.
Okay. That's where you'll be shortly.
And I'm in group 6 with Isaac and Grayson. Or group 8.
Okay. Sounds good. And Isaac and Grayson in 8, I think. We'll see if it works.